There's a wall, not a physical wall you could crash into, but a boundary so absolute that no signal, no light, no information of any kind has ever crossed it. It's called the edge of the observable universe, and it sits about 46 billion light-years away from where you're sitting right now. Here's the thing that keeps physicists up at night. That wall isn't the end. It can't be. And what comes after it is so strange, so fundamentally different from anything we can see or measure, that the word weird doesn't even come close to covering it. So today, we're going to go there, past the edge, past everything we know, and by the end of this, your understanding of reality is going to be a little bit broken in the best possible way. Let's talk about what's actually out there. Before we get to what's beyond the universe, you need to understand why we can't see it. The universe is 13.8 billion years old. That's how long ago the Big Bang happened. So in theory, you might think light has only had 13.8 billion years to travel, which means the edge of the observable universe should be 13.8 billion light-years away. But it's not. It's 46 billion light-years away. And that extra distance is the first clue that something deeply strange is going on. Space itself is expanding. It has been since the very beginning. The galaxies on the edge of what we can see aren't just moving away from us. The space between us and them is stretching, pulling them further and further beyond any possible observation. There are galaxies that existed in our observable universe a billion years ago that are now completely, permanently gone from our view. Not because they moved, because the space between us expanded faster than light could cross it, and that's just inside the observable universe. Beyond that wall, space presumably keeps going, but we will never, ever see it. So what's out there? Here's where it gets interesting. If the universe is infinite, and the current evidence leans that way, then everything that can happen does happen. Somewhere, infinitely far from where you're sitting, there is an exact copy of you. Same face, same memories, same slightly embarrassing thing you did in middle school. An identical copy, reading an identical script, in an identical room. This isn't science fiction. This is a direct mathematical consequence of infinity. Think about a deck of cards. 52 cards, finite number of arrangements. If you shuffle that deck enough times, you will eventually get the same order twice. Now imagine a universe with a finite number of possible particle configurations spread across infinite space. The configurations have to repeat. There is no way around it. Cosmologists call this a level 1 multiverse, and it's probably the least wild version of what might exist beyond our cosmic horizon. Because once you accept that space goes on forever beyond what we can see, things get significantly stranger from there. In the 1980s, a physicist named Alan Guth came up with a theory to explain a few puzzling things about the early universe. He called it inflation, and the basic idea is that in the first tiny fractions of a second after the Big Bang, the universe expanded at a rate so fast it makes today's expansion look like standing still. We're talking about going from something smaller than a proton to something roughly the size of a grapefruit in less than a billionth of a trillionth of a trillionth of a second. But here's where inflation gets uncomfortable. According to the math, inflation doesn't just stop. It stops in some places but keeps going in others. Eternally. Which means the Big Bang wasn't a single event. It was more like a process that's still running, constantly inflating new regions of space, each of which becomes its own universe with its own physical laws, its own constants, maybe even different dimensions. This is called eternal inflation, and it implies that our universe is a bubble. A single bubble in an ocean of other bubbles, each one separated from the others by expanding space so vast that travel between them is forever impossible. And here's the part that takes a minute to absorb. Each of those bubble universes could have completely different physics. In some of them, the electron might have a different mass. In others, the force holding atoms together might be slightly weaker, meaning no stars ever form, no planets, no life of any kind. just cold hydrogen drifting through empty dark space forever. In others, gravity might work differently. In some, there might be fewer than 3 dimensions of space. Our universe isn't just one of many. It may be one of an infinite number, almost all of which are completely hostile to anything resembling existence. We got lucky, or something selected us, and we genuinely don't know which. Now, if the multiverse of eternal inflation doesn't shake you, string theory wants a word. String theory, still unproven but taken seriously by a significant portion of theoretical physicists, suggests that the fundamental building blocks of reality aren't particles. They're tiny vibrating loops of energy, strings, and the way they vibrate determines what kind of particle they become. A different vibration frequency makes an electron instead of a quark. But for the math of string theory to work, the universe needs more dimensions than the 3 we experience plus time. It needs 10 or 11 dimensions. The extra ones are curled up so small we'd never detect them directly, but they're there in the equations. And the number of ways those extra dimensions can be configured is roughly 10 to the power of 500. That's a number so large it doesn't have a name. It's larger than the number of atoms in the observable universe, by so much that comparing the two is almost meaningless. Each configuration gives you a different universe with different laws, and eternal inflation could, in principle, produce all of them. Every possible configuration of dimensions, every possible set of physical constants, every possible version of reality, all existing somewhere in an infinite landscape of universes. This is sometimes called the string theory landscape, and it raises a question that physicists genuinely argue about at conferences. If every possible universe exists, then our universe being fine-tuned for life isn't a miracle or a mystery. It's just selection. Of course, we're in a universe that supports life because we can only observe universes that support observers. Every other configuration exists, but nobody is there to ask questions about it. Some physicists find that deeply satisfying. Others find it deeply unsatisfying because a theory that predicts everything essentially predicts nothing. You can't test it, you can't falsify it, and science runs on falsification. Which brings us to the hardest question of all. What if the universe doesn't have an outside? There's a version of cosmology in which the question, what's beyond the universe, is like asking what's north of the North Pole. The question sounds meaningful, but isn't. If the universe is everything, if space and time themselves began at the Big Bang, and there was no before and there is no outside, then beyond the universe is nothing. Not empty space, not darkness, not cold vacuum, nothing. The absence of space entirely. This is genuinely hard for human brains to process because our brains evolved to understand space, to navigate it, to build shelters in it, to throw things through it. We have no intuition for the absence of space. We imagine nothing, and we picture a dark, empty room. But that room is still space. True nothing is something our minds can gesture toward, but never actually hold. Stephen Hawking and James Hartley proposed a model where time itself becomes a spatial dimension near the Big Bang, which means asking what came before the Big Bang is like asking what's south of the South Pole. But here's why that answer isn't fully satisfying either. Because if inflation happened, and the evidence strongly suggests it did, then there is space beyond our cosmic horizon. Real space, real galaxies, real matter, extending further than we can ever see. So the universe has an outside, we just can't reach it. And that outside goes on, by current best estimates, at least 10 to the power of 10, to the power of 115 times larger than the observable universe. Numbers like that stop meaning anything to human intuition, but they're the best physics has. Here's where this leaves us. We are living in a tiny, observable bubble inside a vast and possibly infinite universe, which may itself be one bubble in an infinite sea of universes, each one governed by different physics, none of which we can ever directly observe or communicate with. The stuff we can see and measure and study, everything from the planets to the galaxies to the cosmic microwave background, represents a vanishingly small fraction of what almost certainly exists. And the question of what's beyond all of it, what the whole thing is embedded in, whether embedded in something even makes sense, is a question that may be permanently beyond the reach of human science. Not because we aren't smart enough, but because information from beyond our cosmic horizon cannot, even in principle, ever reach us. We are, in a very real sense, trapped inside what we can know. And yet here we are, building telescopes, running equations, proposing theories, trying to understand something that may be fundamentally unobservable. That drive to push past the edge of what's knowable might be the strangest thing in the universe. And as far as we know, it only exists in a thin layer of carbon-based chemistry on one small planet in one ordinary galaxy, somewhere in the middle of all this. If that doesn't break your brain just a little, I don't know what will.